So thank you for the invitation and a very interesting conference where I'm learning a lot. So this is about the notion of extensional definiteness or extensional determinateness that has come up a little bit in some earlier talks. And about two-thirds of what I do will be based on joint work with Laura. But I will also veer off from joint work and speak for myself in ways that she may not necessarily agree with. That's why there is this formulation of incorporating joint work with Laura. Much of it is, not all. So I wanted to start just by remembering my recently deceased PhD supervisor, Charles Parsons. Died on the 19th of April, so very, very recently. Fantastic supervisor, and here depicted on a philosophical hike in Norway, right outside of Oslo. So he's been a big inspiration, of course, for much of this work. And the notion of definiteness comes up quite a lot in mathematics and philosophy of mathematics and beyond. I'll give you many examples shortly. Here is a kind of overview of the two main families of notions of definiteness that I will be interested in. So you could look at a concept F and ask, what is it for that concept, or just an open formula for that matter, to be definite? And I'll distinguish between the two main families. So intensional definiteness of this concept or open formula, which is when the formula is definite when you apply it to objects one by one. So I guess one way to think about that is that questions of this form, is this object or that object an F? Do you get a definite answer, yes or no? Okay, so this is when you have definite answers to individual questions about this thing or that thing being F. Extensional definiteness is more demanding. So here you look at all the F's taken together, and you ask, is it definite somehow which are all the F's? And if that is definite, then there would be clear answers to questions about whether all the F's are thus and so or not. And these notions have really been run together in much of at least the philosophical literature. I think some of the technical literature too. So here's the plan then to give you some examples of talk about definiteness in Cantor and Zermelo as a warm-up. My main interest will be in Weil on the notion of extensional definiteness, or in English translation of the works of Weil, extensional determinateness. So I'll tell you about the notion that Weil has here. That's part two. Part three is to tell you something about what Weil takes to be extensionally determinate and what not. So one can have the notion and then agree with Weil on what falls under the notion or not. And in part four, I will speak more my own mind. Using the Weilian notion of extensional determinateness, but to some extent disagreeing with Weil on what is and is not extensionally determinate. That's a plan. So the warm-ups first, just to give you a sense, and also show that this talk of definiteness is not just some philosophical add-on to mathematics. It's right there in mathematical practice. So here's an early characterization of sets by Cantor. So I call a manifold or an aggregate a set of elements which belongs to any conceptual sphere, well-defined. Okay, so the set is well-defined if on the basis of its definition and in consequence of the logical principle of extruded middle, it must be recognized, and here's the important part, that it is internally determined whether an arbitrary object of this conceptual sphere belongs to the manifold or not, right? So pick an object of the relevant sort, and then it needs to be determined whether it's in the set or out. right? So this is a definite question asked of an individual object. So what Laura and I call intensional definiteness. And also whether two objects in the set, in spite of formal differences in the manner in which they're given, are equal or not. I think the most important thing is the arbitrary object either being determinately in the set or determinately out. So this is thinking of sets being well-defined as a matter of the set being intentionally definite, or the formula defining the attempted set being intentionally definite. And then a little bit later in the most famous of the Cantorian explications of, or definitions even of set, you find the following. So by a set, we understand every collection into a whole, big M, of determinate, well-distinguished objects, little m, of our intuition or our thought, which will be called the elements of big M. And we write this as big M is the set of these things, little m. So that's not a singleton set. What's going on here is really that there are some objects, note the plural, and you get the elements, again, plural. So one way of explicating this, which I like, is to use so-called plural logic, where you have double variables. Think of them as a kind of second-order variable if you're not familiar with them. The variable set can have many values instead of just one, right? So plural pronouns would be an example to keep in mind. When I say they addressing you, I refer to each one of you, but not necessarily to a set of you. So then the idea would be that you take some object, plural, MM, and then collect those into a set. You gather them. It's a Zusammenfassung in Cantor's German. Okay, so what kind of definiteness is required here? What Cantor writes is that you have determinate, well-distinguished objects. So what is it for these objects to be determinate? And then when you think of the plural analysis, you see immediately that there are two ways of analyzing this, depending on how you take that plural predication of some things being determinate and well distinguished. So plural predications admit of two readings in general. There's a distributive reading where some things have a property if each and every one of them has that property. Okay, so they are French is true if and only if every one of them is French, right? That's distributive. And then collective is where the predication doesn't distribute to individual elements or individual objects. So they surrounded the building or they cooperate. That's saying something about the things in question collectively. So that's non-distributive. So you have the two readings here, and it's not totally clear, but the fact that they are to be collected together as a whole suggests to some extent that it is a collective reading that is intended. And if so, the definiteness property is something that pertains to the many things, the many objects that would be elements of the candidate set as a whole. So that would make this an extensional definiteness idea. And then last Cantor passages come just 2 years later, where he even comments on the passage you just saw. And writes first, this is after the paradoxes had started to be discussed. And he writes to Hilbert to explain why his theory, his way of thinking about sets is not affected by the paradoxes. So I say of a set that it can be thought of as finished if it is possible without contradiction, as can be done with finite sets, to think of all its elements as existing together And so to think of the set itself as a compounded thing for itself, or in other words, if it's possible to imagine the set as actually existing with the totality of its elements. So I think there are two things to note here. One is the use of this temporal and modal language of being finished, existing together, possibly existing together. So temporal and modal language, and also the fact that here there's very clearly collective predication going on. Existing together is a collective predication. So here there is an idea of definiteness that belongs to the extensional version. And not just that, we get a sense now of how this notion of extensional definiteness is to be understood. It's a matter of being finished, as Cantor puts it, or completable. So if you think of the successive definition of sets through gathering many into one as a kind of process that can be iterated, then some objects can be finished in that process and in that sense be eligible for being gathered together into a set yet again. And he goes on to, I like this, say that he likes the French and the Italian words for sets. And that so nicely brings out the idea of gathering many into one. And then comments on the definition I gave you on the previous slide, that so too in the first article, the quote on the previous slide, I define set meaning thereby only the finite or transfinite at the very beginning as an assembling together, Zusammenfassung. But an assembling together is only possible if an existing together is possible. Right? So first the candidate, the members of the candidate set have to exist together. So there's just got to be Zusammensein, and then you can have a Zusammenfassung. Then you can gather them together or assemble them together. Okay, so very suggestive, I think, of what it takes to be a set, what a set is, but it's kind of vague and promissory and underdeveloped. So one way to go with it is to actually do something that Charles Parsons already started to do, and explicate Cantor's idea using modal language, modal logic. So he had the modal glosses, and he seemed to be onto something. But why don't we actually use the resources of modal logic to try to make this a bit clearer and spell this out, make it into something more workable? So you can then have the principle that you use modal operators to reason about the successive definition of more and more sets through gathering together, that operation. So then you would have the claim that necessarily, wherever you are in that process, when you come across some things in that process that are all there, they coexist, then they can be gathered together. So you take another step in the process, so it's possible that they're gathered together as a set. And you could explicate this using a logic of plurals for one thing, and modal resources, of course. So there's a lot to be said here, and I'm going to be very, very brief. Since this isn't my main topic, it's just to give you a little bit of a sense of this Cantorian notion of completability and how it can be spelled out technically to a satisfactory extent. So you could use a modal logic known as S4.2. The point two business captures the idea that the accessibility relation here is convergent. So if there are two ways to go, you can bring the two possibilities together again. And then the pluralities, or the many things, they are thought of as some things that coexist. Right? So they are all there at some stage of this process. So they need to be tracked then rigidly as you go from one world to another. Right? So when you have a plurality, that plurality cannot gain members as you go to a more populous world. Here I'm indulging in world talk to convey the idea. This can all be expressed just using the resources of modal logic. And when you do so, you get a nice notion of being completable, which is this one, that it's possible to get some things which are all and only the phi's that you will ever come across. That is what it means for phi to be completable, or the phi's to be completable, or in Cantorian language to be a consistent multiplicity. You can translate then the language of ordinary non-modal set theory into this modal language that we use here to explicate these Cantorian ideas in this way. And you actually get to interpret quite a lot of set theory. And if you strengthen the theory somewhat beyond what I've laid out here or hinted at here, you can interpret all of ZFC set theory. Okay, so that's contour on the two notions, intensional and extensional definiteness, with extensional definiteness understood as completability in that sense. So a little bit about Zermelo then. Here's the famous statement of separation from the 08 paper. Whenever the propositional function phi of x is definite for all elements of a set big M, note the Cantorian formalism, big M possesses a subset M sub phi containing as elements precisely those elements X of big M for which that condition is true. And two things are going on here, of course. So one is that you got to start with a set, which you then cut down. That's a big restriction. And then secondly, the propositional function needs to be definite for all, or I would say each element of M. So that needs to be intentionally definite, the condition that you use to cut the set down. So that's an intentional definiteness idea. Then in the 1930 paper on quasi-categoricity, the models of second-order ZF are the normal domains, and they are glossed then in a very Cantorian kind of language. So as completions, as closed, which is pretty close to the Cantorian finished. They have well-defined cardinality and rank. So this looks very much like extensional definiteness, that they collectively, the members of the set collectively are definite. Definite enough to be closed or completed or have well-defined cardinalities and ranks. And then here you get more information about what is actually completable. So answering complaints that were started to be made in the literature that Cantor's remarks are suggestive but totally underdeveloped and doesn't give us much practical help, which is true. And they can then be spelled out modally, as I hinted at, or you could go Zermelo's route here. So there are things to do with this notion of completability. Okay, so on then to Weil's notion of extensional definiteness. And I'm going to start then with Weil on the infinite in general. And a little bit of this we saw already yesterday, that Weil regards the infinite as inexhaustible. So inexhaustibility is essential to the infinity claims. And here's a lovely passage where it comes up in an even more striking way. So it's a kind of potentialism, so that the domain of mathematical objects is potential, forever growing, or in the making. So the deepest root of the problem lies elsewhere. A field of possibilities open into infinity has been mistaken for a closed realm, closed again, of things existing in themselves. As Brouwer pointed out, this is a fallacy, the full and original sin of set theory, even if no paradoxes result from it. Okay, so one thing is guarding against the paradoxes, and another thing is proceeding in a sound, defensible way. So even if you're lucky and no paradoxes result from failing to heed this advice, you should take this seriously. That's That's the idea. So the infinite is potential only. It's a field of possibilities open into infinity. The infinite is inexhaustible. So the picture you get here is that all interesting, all infinite mathematical domains are incompletable in the Cantorian sense of completable. Right? They're inexhaustible. They're fields of possibilities, open fields of possibilities, not closed. Okay, so you may think here that, wow, so they're incompletable. Completable was a notion of extensional definiteness. So everything infinite becomes extensionally indefinite. That's how it seems at this point. Since they're not extensionally definite in the Cantorian sense. But that is not Weyl's view, and this is where it's getting really fascinating. So according to Weil, incompletable domains really come in two kinds. Right? So one can be incompletable and yet, in a sense, in a different sense, in a non-Cantorian sense, be extensionally determinate. So that's something Laura and I argued in a paper that recently appeared. And here's the first step towards that idea of extensional determinateness. Just as a little terminological note here, I'm going to use extensional definiteness for the broad family that can be understood in the Cantorian sense of completability or Weil sense, and then reserve extensionally determinate for the Weilian notion. I'll try to qualify the Weilian one, or it'll be clear from context. Anyway, here's the first step that Weil takes towards characterizing this new notion of extensional determinateness. So concepts can be clearly and unambiguously defined, but that does not imply that the concept is extensionally determinate, i.e. that it's meaningful to speak of the existent objects falling under it as an ideally closed aggregate which is intrinsically determined and demarcated. Not super clear, it's suggestive. I like this since people sometimes say that, oh, you philosophers, I'm one of them, use all this vague language to kind of approximate an idea. But here you see one of the top mathematicians do exactly the same thing. So start in a very vague, suggestive way and gradually pin it down. So the bit I like particularly here is demarcated. So the picture we're headed towards is that the Cantorian notion of a completable, that's a strong notion of definiteness. That's very demanding. And then there's a less demanding notion where a domain can be incompletable, yet still be demarcated. So completable is that you have all the members of the domain available, okay? And incompletable is that there's only a conceptual way of specifying the domain, namely in terms of how it is generated. But you can specify how it's generated in a way that demarcates what it is that you may generate in that way. Okay, so it makes sense to be demarcated even though one is not complete or completable. Okay, this is where things get clear. So now we're moving towards a logical articulation of this idea of being demarcated. So suppose P is a property pertinent to the objects falling under a concept C. If the concept C is extensionally determinate, then not only the question, does A have the property P, or some arbitrarily chosen object A, not only that possesses a sense which is intrinsically clear. So not only is P intentionally definite on each member of C, not only intentional definiteness, but also the existential question, is there an object falling under C which has the property P, has a sense which is intrinsically clear? Okay, so it takes a bit of time to parse this. The language is tough, but the idea then is that there's something more demanding than just uh, P being well defined point by point. So admitting definite answers to individual questions of is A P, is B a P, and so on. But you can talk about all the C's. Are all of them thus and so? Are all of them P? Or is there some object among all the C's, which is a P? Okay. The last bit that remains is to take this notion of having an intrinsically clear sense and pin that down. And Weil does that actually. So a question has an intrinsically clear sense when it addresses an existing state of affairs that allows one to answer the question with yes or no. So what we would call bivalence, that either the question that we're looking at here is true, or it's got a true answer, or it's got a false, or it's true, or the statement is true or false. So here's yet another way to put it, just to give you a couple of different formulations. Suppose a concept C is extensionally determinate. What does that do for you? Well, if you've got a concept P, which is intentionally definite, so there's an answer to every question of the form is a P, then the question, is there among all the C's a P, also has a determinate answer. Right? So the property of having determinate answers is preserved under quantification over all the C's. That is what it is for C to be extensionally determinate. The property of being such that one can quantify over that collection, preserving the property of having a determinate answer, yes or no. Okay. One thing one can do here is to press on and say that bivalence is fine. It's a notion that lives in the meta language, but we could actually get this into the object language by using intuitionistic logic. And bivalence would then correspond, of course, to law of excluded middle. And then you would get this formal analysis of extensional determinateness in the object language, which is nice. So concept C is extensionally determinate if quantification restricted to C preserves the property of LAM holding. Okay, so if you got a property P, which is intentionally definite, so every individual question is this or that a P, has a determinate answer, then one can determinately quantify over all the C's and ask, is there a P among all of them? And that too has a determinate answer. So we arrive now through this sequence of steps of explicating ideas in Weil at a view that, or slogan that was formulated by Pfefferman, that what's definite is the domain of classical logic, what's not is the domain of intuitionistic logic. Okay, so one last thing on Weil here. So I told you that completability is more demanding than extensional determinateness. Here's a way to make that even sharper. So generalizations over a completable domain can be understood in what I like to call an instantial manner. So a universal generalization is true when and because each and every object in that domain has the relevant property, or is the relevant way, yeah. So as Weil puts it here, we have these elements, so to speak, laid out in front of us. That's what completability does. So that in order to find out whether an object of this or that kind exists in the set, we only need to go through them one by one like a police officer in his files. Right? That's what you can do when the domain is completable. You just sort through it. And then intentional definiteness would ensure that the quantified question is also definite. So the domain over which you're quantifying is extensionally determinate. So the implication holds. Okay, now on to what Weil takes to be extensionally determinate. So I've told you so far just about the concept that Weil has of being extensionally determinate, starting with this intuitive, suggestive idea of being demarcated as something worth caring about, but less demanding than being completable. And that got pinned down in this formal way. So that gives us a very abstract, very general notion of extensional determinateness, a notion that I think is very, very good and very useful. And here's now in part 3 what Weil takes to have that property of being extensionally determinate and whatnot. It's all really summarized in this passage. So the intuition of iteration assures us that the concept natural number is extensionally determinate. So that is demarcated. However, the universal concept object is not extensionally determinate. That may be not too surprising or shocking. Nor is the concept property, again, not too bad, nor even property of the natural numbers. And when you keep in mind that sets of natural numbers have to be characterized by properties of natural numbers, if the domain of properties of natural numbers isn't extensionally determinate, then nor would be all the sets of natural numbers. So the last bit has real force. Okay, so here's a little bit more about what falls on the right side of being extensively determinate. So we can say that the domain is ED if the concept that defines it is ED. And then induction is how the obvious way to get an extensionally determinate domain. And that's what we do with the natural numbers. And then the intuition of iteration assures us then that this concept is extensionally determinate. Okay. And also one thing to keep in mind here is kind of how this interacts with the notion of having pinned down all members of the domain. Okay, so have we pinned down all members or demarcated all members of the domain of natural numbers? Well, yes, we have. Since if you later on admit more objects, say by also generating transfinite ordinals, then no new objects will be admitted as natural numbers. So the intuitive idea of demarcated fits here. Okay, then that was the paradigm example of what fits on the good side of being extensively determinate. And here's a case of something, or working towards a case of something that doesn't fall on that side. So what about the domain of all sets of natural numbers? Couldn't that too be demarcated, one might have thought? But here Weil rejects the combinatorial conception of set. So the notion of an infinite set as a gathering brought together by infinitely many individual acts of selection, assembled and surveyed as a whole by consciousness, is nonsensical because inexhaustibility is essential to the infinite. Okay, so this is typical of Weil. So he's not only skeptical of this combinatorial idea applied to the infinite, he really comes out swinging against it and says that it's nonsensical. It's not only sort of poorly justified or unnecessary, but it's nonsense. So this will be one of the places where I part ways with Weil. I think he's far too harsh here. We'll get to that. So since an infinite set is incompletable, to describe it, one needs a rule that indicates the properties which apply to the elements of the set and to no others. That's what you need to do if you want to talk about sets taken from an infinite domain. Since this combinatorial or quasi-combinatorial idea of just an arbitrary selection of objects, that is illegitimate nonsense. So what do we do instead? Well, this is familiar territory to you guys. So what we do is to define predicative sets of natural numbers. Guys, so you have this process of starting with the basic category, say the natural numbers, some primitive relations on these objects, and then you gradually build up or construct, define larger and larger collections of sets that are determinate, that are extensionally determinate. Okay, so each predicative set of natural numbers is extensionally determinate because it's been carefully constructed in a way that ensures that in that construction process, every step you took preserves extensional determinateness. So each predicative set of numbers is extensionally determinate. But now, then we get to the question of what about all such sets? So the domain of all of them. Is that extensionally determinate as well? And we saw from the opening quote that Weil says no. He argues that the answer is negative. It's a pretty bizarre and, to be Weil, oddly hedged argument in Das Continuum, but in the Grundlagen case. But I'm going to give you soon a way to reconstruct an argument to that effect. But let's just pause to think a little bit about what would have happened if the domain of all sets of natural numbers had been extensionally determinate. Extensional determinateness is a property that you can quantify over that domain and preserve having an intrinsically clear sense. Yeah. So if you could do that, then you could quantify freely over this domain using second-order quantifiers or set quantifiers and still have a condition that is determinate in the sense of having this determined yes-no answer, which is applied to the extensionally determinate domain of natural numbers. So then you could have done comprehension on any condition in the language of second-order arithmetic. So predicativity restrictions would drop by the wayside. Now, here's my way of reconstructing an argument to that effect. Why the domain of all sets of natural numbers is not ED. It's an argument from indefinite extensibility, I call it, in the Dometian sense, for those of you who are familiar with that. And first, we observe that when we construct predicative sets of natural numbers, then every ED domain, extensively determinate domain of sets that you can construct in this way, can be coded by a single set of naturals whose sections then represent all the sets in that domain that you have constructed. Okay, that you can show yourself of. And then for every such ED domain of sets of numbers that you have constructed predicatively, you can then diagonalize out. So that can't capture all the sets of natural numbers. Okay, so for everyone you can construct predicatively, it doesn't get all of the sets of natural numbers. So the last premise we need is that every extensionally determinate domain of sets of numbers can be obtained in this way by predicative construction. So this is where you need to reject the combinatorial conception as applied to the natural numbers. Since if you did have that, you could say that, look, I'm going to apply the combinatorial notion here, and that gives me an ED domain of sets of numbers. So the first two premises are well supported. The third premise is one that Weil is more than happy to endorse, but can be contested. Here's a little bit about how when you go for the analysis of extensional determinateness in Weil sense in the object language using intuitionistic logic, how things would look when you take that view, that quantification over the natural numbers is, or the natural numbers are extensionally determinate, so you can quantify classically over those, but not so the domain of sets of numbers. So then all atomic predications are decidable. That's ensured by the construction procedure. Then the cache value of the claim that the natural numbers are extensively determinate is this bounded omniscience claim. Right? So if you have a question that you get definitive answers to when you ask individual, are you thus and so? Is that this or that object thus and so? Then you can quantify over all the natural numbers and still get determinate answers. But by contrast, we don't, of course, have omniscience for sets of natural numbers, since they are not, that domain is not extensionally determinate. Okay, so the last bit I want to address is what one might do with this notion of extensional determinateness that we have from Weil, this very abstract logical notion, without necessarily agreeing with Weil on what is determinate in that way. Okay, so what is and what is not extensively determinate in Weil's sense? So using Weil's notion, but reserving to the right to disagree with Weil on what is and is not ED in that sense. So what might ensure that the domain is extensively determinate? Well, the domain could be externally given, right? So the domain of all stars or all physical objects, or if you think that's well defined, that's externally given. It's complete, presumably, all the stars are there. Of course, yeah, we get into metaphysics, but that's a reasonable assumption to take. Or you could even have an externally given space of possibilities when you go for one of these potentialist analyses of this. So think about Aristotle on potential infinity. If the modality he uses is determinate enough, comes with a determinate space of possibilities, then that would give you an assurance of extensional determinateness. Right? So that's one way to get it, just by appealing to something external to mathematics. And then here's Weil in the Grundlagenkrise paper, reflecting on how he was thinking in Das Continuum. And he writes that if I run through the sequence of numbers and terminate if I find a number with a property E, then this termination will either occur at some point or it will not. That is, it is so, or it is not so, without any wavering and without a third possibility. Okay, so here you have the modality of continuing onwards and onwards and onwards in time. Okay, and then there's a factor that either you will hit upon an E or you will not. So one might think that this is using time as an externally given space of possibilities or indices in the modality of time, possibly. Not entirely clear. But what we want ultimately is to not appeal to extra mathematical considerations here, but have some intra-mathematical assurance of extensional determinateness. And this is where induction comes in. The obvious way, as you saw from Weil himself, to define an extensively determinate domain is as a minimal closure of under some generating operation or operations. Right? So you start with some domain that is ED in whichever way, And then you apply this generating operation or operations to every element of the domain or tuple from the domain, and you take the minimal closure by adopting some induction scheme, right? And then it looks like that is a way of demarcating that domain. So ensuring that the domain is extensively determined. But what can we, and here we come to the big fork in the road. So what can we do when giving these kinds of inductive characterizations of domains that we're interested in? So is the combinatorial concept of an arbitrary subcollection sufficiently determinate to be applicable to infinite domains? Right, that's a question. So if you answer no to that question, then you're in the reasoning that we saw Weil engage with in the previous part, right? So then sets need to be predicative sets and the story you saw. If, on the other hand, you answer yes here, it's a very different picture. So if the quasi-combinatorial notion is determined enough to be applicable to infinite domains, then you could use that for the purposes of giving inductive characterizations of domains as extensively determinate, as on the famous iterative conception of sets. So I put down here the famous Gödel quote on that. I think the key bit is that you think of the sets as obtained by iterated application of the operation set off, right? And that's never caused any difficulties, right? So you have an operation set off, which you apply to some well-defined objects. Look how Cantorian this is. So you have some, plural, well-defined objects, which you can apply the set-off operation to obtain their set, right? So if you have quasi-combinatorial reasoning to give you all the many objects to which you can apply this set-off operation, then you apply it successively, and you generate the famous cumulative hierarchy of sets, as on the iterative conception. So what I propose to do in the remaining time now is to proceed on the assumption that the combinatorial notion is determinate enough to be applicable to infinite domains, very much in the spirit of the famous Paul Bernays on Platonism and mathematics paper. So how definite is the hierarchy of all sets if you make that assumption that quasi-combinatorial ways of thinking about infinite domains is permissible? So how definite in the different notions of definiteness that we have seen now is the domain or hierarchy of all sets? So one thing we know is that the hierarchy of all sets cannot be completable in the Cantorian sense, since if it were, then all the sets would exist as this vast plurality of coexisting things, all available to apply the operation set off to yet again and go on. So you wouldn't have had all the sets after all. So the domain of all sets cannot be completable in the Cantorian sense. But now that we have two notions of extensional definiteness to play with, that's not the end of the story. So in earlier work on my own and by others on explicating these potentialist ideas in set theory, so the potentialist way of thinking about set theory and of taking the suggestive Cantorian idea seriously, we reach the conclusion that the domain of all sets cannot be completable. That's fine. But now we have the next step down of being extensionally determinate in Weil sense. And for that reason, admitting classical quantification over that domain. So that becomes a pressing question now that this notion has been articulated clearly in a way that wasn't clear to me, at least, back when I worked on this. So here's the thinking that motivated me, and I think others, to think that the hierarchy of sets is extensionally determinate. Because it looks like it's just this hierarchy is generated inductively, right? So what you do is to start with the complete domain of elements, yeah, and then you have this one generating operation. Take some things that you come across, right? Take any coexistent things, to use that Cantorian language, and apply the operation of Zusammenfassung or set off. Right? So that is the generating operation. And then you take the minimal closure onto that generating operation, or you look at everything obtainable in that way. And how do you think and reason about taking everything obtainable in that way and nothing more? Induction, of course, as usual. So if we suppose that every element is phi, and that phi is preserved from each of some things to the set of those things, then everything, or at least every set, depending on whether you admit non-sets, is also a phi. Right? So it looks like you're just giving an inductive characterization of the domain, and it should be ED and determinate enough to admit of classical quantification. So the last thing I wanted to mention to you is some considerations that has led me to think that that is not so. It seems ED for the domain of all sets, but it cannot be. And one way to bring that out is to think about what happens when you add predicative classes on top of quasi-combinatorial sets. Right? So we're going to do now kind of the set theoretic analog of what one does when you add predicative classes of natural numbers in a two-sorted manner. Now we're going to add predicative classes of the Cantorian sets, yeah, and see what happens. And then we're supposing now that the domain of all sets is extensionally determinate. Then you can, of course, characterize class well-orderings that extend way beyond big omega. Just like in the case of predicative sets of numbers, you can have well-orderings that extend beyond little omega. Now you can go beyond big omega. And just like in the case of predicative classes of numbers, you iterate beyond class generation, beyond little omega. Here we can iterate class generation beyond big omega. Why not? Since you have these kind of classical spines of stages along which to iterate. So by analogy with the case of predicative classes of numbers, you should do the same thing here and iterate class formation along these class well-orderings. So you iterate beyond big omega. But then, hey, if you admit iteration of class formation in this way, you should also admit iteration of set formation beyond big omega. But that makes no sense, since then you have you couldn't have all the sets after all. So this is a way then of seeing that the assumption that we have a domain, an ED domain of all sets, seemed reasonable, why that destabilizes. So the conclusion here is that even if you follow Bernays and say that if only for the sake of argument, I go along with the assumption that quasi-combinatorial reasoning is okay, right? We grant that. Then you get a bunch of interesting ED domains, of course, so the domain of sets of numbers, sets and sets of numbers, and so on. But the hierarchy of all sets, we've known for some time, I would say that that cannot be completable, but nor can it be extensionally determinate, contrary to earlier work and claims of my own. So that's one upshot and value of getting clear on this notion of extensional determinateness from Weil. So what do you do instead? This is very parallel to what we saw in the case of sets or classes of numbers. So now atomic predications involving sets remain decidable. Membership questions and identity questions. You have bounded omniscience for sets, right? So when phi is decidable in each member of a set, then the result of quantifying over all the members of that set too is decidable. And quantification over all sets is only intuitionistic. So familiar semi-intuitionistic logic here. So global quantification goes intuitionistic, but otherwise everything is classical. And this gives you the resources now to block the iteration of class, or for that matter, set formation beyond big omega, which is what we wanted to do. So predicated classes have to be decidable as to membership, and that is no longer guaranteed were you to iterate to and beyond big omega, since then you're engaging in quantification, no longer subject to classical logic. So the needed decidability for membership in the would-be class would not be available. So class iteration is stopped beyond big omega, and a good thing. And likewise, set iteration, set formation beyond big omega is stopped. Since a set needs to, a set is a domain of classical quantification, and the domain of everything up to big omega is not classical. So you don't have what it takes to define a set. So wrapping up then, three notions of definiteness ordered by logical strength, where I think there has been a tendency, well, there have been many conflations in the literature. So people have conflated intentional definiteness with notions on the extensional definiteness side. And there's been conflation of the two different notions of extensional definiteness, the demanding notion of completability and the less demanding one of being demarcated or Weil ED. That's one claim. Next, that Weil's notion of extensional determinateness is particularly nice when you analyze it in intuitionistic logic. So then to be ED is to be a domain of classical quantification, and then you're in the setting of these semi-intuitionistic logics. And Weil's notion of ED plays a key role also in the analysis of predicativity. And the last point that forces me to correct things I've said before, that even if we permit quasi-combinatorial reasoning, then thinking clearly about this and having these two notions clearly distinguished, you can see that the hierarchy of all sets fails not only to achieve the highest degree of extensional definiteness, but even the Weil extensional determinateness, less demanding notion. Thank you.